All right, in this worked example, we're going to take a look at question 3 from the October-November administration of paper 21, 2015, coming from ACE Physics syllabus code 9702. The question reads, an object is moved from point P to point R, either by a direct path or by the path P to Q to R, as shown in the figure. P and Q are on the same horizontal level. R is vertically above Q. Explain whether the work done moving the object against the gravitational field is the same or different along paths PR and PQR. A key to understanding this is against the gravitational field. And so the horizontal level, PQ, vertical, they're showing us is this way. And so we know that gravity always acts straight down. If we lifted the object along this path from P to R, then we might be sort of exerting a force on it this way. But the only work we're doing against the gravitational field is the component of that force that's acting against the gravity, right? And so there's the force vector, but there's a component that is this way. So we can kind of think about it like there's if it's going up and to the right, there's a component up, and there's a component to the right. And so only the vertical component, of this sort of this force vector here is going to contribute to the work. If we lift the object, if we take the path P to Q to R, the whole time that we're sort of moving the object from P to Q, we're doing no work against gravity because we're moving the entire thing sort of horizontally. So if gravity is acting against it this way and we exert a vector this way, there is no component of our force that's doing work against gravity, that's acting against gravity. It's only once we get to Q that we lift it directly vertically, then all of our force vector sort of is working against gravity. In both of those situations, the work that we're doing against gravity is indeed the same, because it's just kind of like you either do, you exert a force all the way from P to Q, sort of up this way, all the while a component of your force is sort of working against gravity, or you move the object to Q and then you do all the work against gravity. But the work that's being done, you could either think about as like force times this displacement, so all the force acting this way times this displacement, or a component of the work, right, that's acting up over the entire, sort of displacement. Say like the displacement is still from P to R, right? We're still doing the same work against gravity because we've lifted it to the same height, R. The work done against the gravitational field is the same because only the component of force acting in the direction of displacement contributes to work. So some kind of an explanation like that. Question goes on to give us a figure here. Again, this is recorded, so you can always pause it and read through that at your leisure. A ball is thrown with an initial velocity v at an angle theta to the horizontal, as shown in figure 3.2. And then it says the variation with time t of the height h of the ball is shown in figure 3.3. So we're given this like a displacement time graph. And then from that, they say use the time to reach maximum height to determine the vertical component v sub v of the velocity of the ball for time t equals 0. So we know that this thing reached, says use the time to reach maximum height. And so we sort of extract that from the figure. Its maximum height is the peak here, and it looks like it neatly corresponds to 1.5 seconds, right? So directly in between 1 and 2, there's the peak right there. So if it reached max height after 1.5 seconds, how can we use that to deduce the initial velocity? T equals 1.5 seconds. And that is where the vertical component of velocity goes to 0. Okay, so at t equals 1.5 seconds, the vertical component of velocity is 0 because that's where gravity has slowed it down to a stop before it speeds it back up in the opposite direction. So we know that's true, we know that's true, and we can assume that this is happening here on Earth with negative 9.81 meters per second squared of acceleration due to gravity. So those are our three knowns, and we're solving for this fourth unknown. The definition of acceleration is the rate of change of velocity. So this, here we want to sort of find out what is the initial velocity u, right? So this is the vertical component velocity at time 0, so the initial component. So we usually rewrite this equation, v equals u plus at, keeping in mind that a is negative compared to the initial velocity vector u that we're launching upwards. And so this becomes 0, the final velocity at max height is equal to the initial velocity. And I'm going to sort of, even though in general I'm solving u, the initial velocity, here they've called it v sub v. So I'll just sort of be consistent with that. So this v is the actual final velocity, like at this time. So sometimes we'll say like v naught, is like the velocity at time 0, or u, it's kind of interchangeable. This is the velocity at time 1.5. So v 1.5 is 0. So this is what we're solving for. And it's going to be minus 9.81 times 1.5 seconds. And so that's the time we extracted from the graph. That's the known acceleration due to gravity. We're saying, how fast was something going if it took gravity, which is this strong, 1.5 seconds to act against it, to equal it out to 0, right? So this term here is the negative of this term, which is our answer. Or you could just think about it like, multiply these two, add it to both sides, right? And sort of just solve it like with algebra. But it's good to sort of think through the equation like, this equation tells me the time that it takes gravity to act on something launched at a non-zero velocity to reach a speed of 0. So it's like, how long does it take gravity to act on it until it cancels it out? Say it again. Oh, well done. Okay. 14.795. And so let's say 715. I might just call that 15, maybe 14.7. The mark scheme will probably, credit this. If we think about sort of the significant digits, 1.50 seconds, I guess we pulled that out of the graph. So we could be, sort of more precise. It's exactly 1.50 seconds, 9.81, 3 significant digits, right? So we'll report it. It says, the horizontal displacement of the ball at t equals 3 seconds is 25.5 meters. On figure 3.4, draw the variation with t of the horizontal displacement x of the ball. So we know that at time t equals 3, it's at 25.5 meters. And so part of this is just sort of reading off this correctly. If there's 20 here and 30 here, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares between it, then each square is 1. And so it's like 21, 22, 23, 24, 25.5 would be right about there. And between 25 and 26. And the horizontal displacement at time 0 was 0 because it wasn't launched yet. The key idea to saying like, is it as simple as connecting the dots? Do I need to like curve this line some way or another? Is it like a wave? What's going on here with the variation as a function of time? So this is range, which is what x is, right? The horizontal displacement is the range, is equal to the constant x component of velocity times the time. And so y equals mx. See how we have X on this axis, we have Y on this axis, and so M is just going to be a slope. It's a linear equation, right? This variable isn't squared, it's not a parabola, it's not, you know, cubed, it's just a linear function. So we're just going to do our best to draw a straight line between those. Hey, that's not too bad. It's pretty good. And so it's just going to be, you know, a straight line. One of the key ideas with graphical analysis is, you know, what can we do with a displacement time graph? The slope of a displacement time graph is velocity. So we see this constant slope with constant velocity. And so if we were to actually find the slope of this, we would know how fast it was going in the X direction. Question goes on to read, for the ball at maximum height, calculate the ratio. Got the potential energy of the ball over the kinetic energy of the ball. It's important to keep in mind that this thing is still moving sideways, okay, when it's at the top of its flight. So the potential energy of the ball is going to be mgh, where h is its maximum height. The kinetic energy of the ball is going to be 1/2 mv squared, where v is the velocity it still possesses, you know, at maximum height. So all of that velocity is due to the x component of velocity, because we remember at the top of its flight at maximum height, its y component went to 0. That's sort of the input that we did in the equation of motion that we used to solve for the initial component of velocity. We can consult the figure to find out the height. It looks like it's right in between these two. So it's kind of like if this is 10 and that's 12 and there's 5 lines, then each one is going to be 0.4, right? Because we have to go up 2 over 5 divisions. And so 2 divided by 5 is 0.4, right? And I always like to count it out to myself. So it'd be 10, 10.4, 10, 10.4, 10.8, 11.2, 11.6, 12. So each one is 0.4. And if we go up to here, it's peaking like right in between these two. So it'd be like 10.4, 10.8. So it's right at 11 meters. If the height is 11 meters and the range was 22.5 meters after 3 seconds, right? That's just sort of taking this data here and saying, well, we just solved for the x component of velocity just using that. 22.5 meters divided by 3 seconds. That means this thing was going in the x direction 7.5 meters every second. So I think that's all the ingredients we need. Show my working clearly down here. So mgh. Note that the mass doesn't matter. It's like, oh, it's impossible. They didn't tell us the mass of this thing. So they want this ratio. The mass sort of just cancels out. So we got gh, 9.81. Now it's both energies, right? And so the units, you know, joules are going to cancel. So I don't really need to worry about the units so much. Everything is in good SI units here to cancel out. 11 meters. Well, don't need to worry about that so much. Was the height. And then we have 1/2, all the velocity was the x component of velocity at maximum height. So we have 1/2 the 7.5 squared. All right, and so that should give us the ratio. 11 times 9.81 is 107.91. And 7.5 squared times 1/2 is 28.125. And so this thing had a lot more potential energy at the top of its flight than it still possessed in kinetic energy. How much more? 107.91 divided by 28.125 looks to be a ratio of 3.8. So it has 3.8 times the potential energy as it did kinetic energy at maximum height, according to those calculations. Question goes on to read, in practice, air resistance is not negligible. State and explain the effect of air resistance on the time taken for the ball to reach maximum height. So if there is wind resistance to contend with here, then it's going to have to sort of crash into, air. There's going to be a force exerted, on it. The time taken to reach maximum height it's going to take it longer to reach maximum height. Or will it? So you say, well, because there's a force acting against it, it's not going to go up as high. It's going to slow down more quickly. And so maybe it'll reach maximum height more quickly, right? It'll take less time to reach maximum height because it has to sort of fight against the resistive force. In other words, there is friction doing work against the friction in the form of air resistance doing work against it there. I'm not sure. I really don't know the answer to this one because the arguments are it's going to take longer because it's got to fight air resistance, right? So it's like slower, but then you say, well, then it's going to go to a lower maximum height. And so it's just going to get there quicker, right? Because it doesn't have to go up as high, right? Because there's air fighting against it. So just imagine if you can use an extreme case. Let's say there's a bunch of air resistance, like a really dense, part of the Earth's atmosphere or something like that. So there's lots of air resistance. And you launch something up into it like a ping pong ball. Well, right away, it's like it can't fight against that. So it's like it's already at maximum height basically immediately. And so you say, oh, it doesn't take long at all, or if there's lots of resistive force. So you can make that argument, but your intuition almost says the opposite. Like you're saying, like, wouldn't it take more time because it's got to sort of fight against this force. So it's like, it's going to be going slower, so it takes more time. But also because it's going slower, gravity, which is always constant, doesn't care about wind, is going to act on it, the same and sort of slow it down faster. So I think the answer is the time will be less because it's going to get to a lower maximum height, more quickly. We'll take a look at a mark scheme to give ourselves feedback on that. So let's say it's like two kind of sensible answers there. 2 marks for that one, and you just kind of do your best to reason your way through it and say, well, my sort of thinking yields this kind of an answer. So I tend to think that I'm not 100% confident, but I tend to think that the answer to this is going to be, it's going to reach maximum height in less time. And again, using an extreme case, like a whole bunch of wind resistance, you can really make the argument that almost immediately after launch, it's going to be at maximum height after almost no time at all, right? If you make that force that the air resistance is exerting against it strong enough, and it doesn't give us a, just say, hey, it's not negligible. Let's make it really not negligible. Let's make it, it doesn't say we can't do that. And so if you can sort of extend that argument to, well, this thing could get to maximum height in almost no time at all if there's really strong wind resistance against it. Then the time taken to get to maximum height would be less. So I'm going to say less because it's going to get, to maximum height more quickly. And that is actually the end of that question. We might take a look at this one next year. This seems like a good one to do. Matter and materials. But first, let's take a look at the mark scheme together. Just because I see it on both the numerator and denominator, I can divide it. So I know the mass is the same. And so it's like m divided by m is 1, and 1 times the rest is just the rest. And so it's kind of like they didn't tell me what the mass was, so I can't substitute it in, but I don't need to because it cancels. And so sometimes students will say, I can't solve this, it's impossible. I know the equation is mgh, I know g, I can read h, they don't give me m, and then they're stumped, but it's like, we'll just keep working, maybe something will happen where you don't need to know it, or there's a way to calculate it from something else. So, all right, that was question number 3. We have, was it 3? Yeah. Work done is force times distance moved in the direction of the force, for no work is done along PQ as there's no distance moved in the direction of force. So the work is the same in the vertical direction as the same distance is moved in the direction of the force. I mean, we kind of basically said that. I'm not sure how clearly we worded it, but we get one or both marks there. We said 15, but we said 14.7 for 3 significant digits, right? We got that. Here they've calculated the displacement was 11, which you can kind of read off the graph, or maybe they use that to calculate V. So I guess they said, oh, S is 11. They read that off the graph. T is 1.5 off the graph, and then plugged it in here to solve for V. So another equation of motion using the data could also get you to this answer of 15. We said it'd be a straight line from the origin up to the coordinates that were given there for time 3 seconds dot range. At maximum height, the velocity in the x direction was 8.5. So they do the ratio mgh to 1/2 mv squared, just as we did. 2 times 9.81 times 11 divided by 8.5 squared. They got 3. What do we got? 3.8. Oh man. So yeah, I blew it there. That's what we call a transfer error. And so everybody watching YouTube is like, oh no, go back. Okay. So put it down in the comments below, you guys. Someone says, hey, at this time you made a mistake. You copied down 22.5. This is why we take a look at the mark scheme. If that were to happen to you when you're sitting for paper 2, the examiners can see what you did and they say, oh, look, they got a transfer error. This person knew all the physics, but got a transfer error. And so we might lose a mark for this, but all the rest of the working was correct. It's like we knew the physics and we just wrote the number down wrong, right? And so when I substituted in maybe this, did we not calculate this? We said it was what, exactly 8 or something? 7 point what? 7.5. So we get the wrong sort of velocity here, which is obviously going to affect the denominator. And so, you need to make that correction. All right, so I just copied it down 25.5, but I wrote 22.5, and sure enough, that's what I calculated with. So you end up getting actually a ratio a little bit less than 3.8, you get 3, and it's because you have to correctly calculate the velocity, in the x direction there. 25.5 divided by 3, not the 22.5 that I mistakenly wrote down with my transfer error there. Thank you for picking up on that. And then we have the deceleration is greater, the resultant force, the weight and the friction is greater, so the time will be less. And again, you can use a problem solving technique called limiting or extreme cases where, just exaggerate the force. If they say, hey, now there's a new force, let's exaggerate it so we can really kind of get to, well, what can we kind of prove will always be the case with a, sort of really strong force. So we put like a hurricane worth of, sort of wind resistance on top of it, throw a ball in the air, and it's like, okay, it's at max height now, immediately after almost no time. And so, yeah, the time would be less. Another takeaway is that it's super easy to make mistakes, to know the physics, but to still make mistakes. And so take care there on all those things like transferring numbers down and just making sure you're getting it right. Every mark counts. All right. This has been another worked example with Dr. Schleich. We'll see you next time.